Alright, so here is our part 2 for the 3-1 assignment. Really not huge because we just have the last two to go over. So, in number 53, I kind of mentioned it before we exited in the last video, but we want to talk about when they're equal. So, I suppose number 53, the easy way would be to graph. And so if we graph both and find the intersection, that works. The problem with that, of course, is that if you're not using something like Desmos, it might be hard to actually see because the intersection points are at like 465,000 and 632,000, or at least the y-intercepts are, so that's kind of intense. So instead of graphing them, you could solve them algebraically. You just got to remember a little bit about your solving. So the one equation, 0350, and then the other equation, 632910. What you could do is to the right side, you could divide over the number. And to the left side, you could divide over the, what is that? Exponential piece, okay? And so if you do that, you end up with 1.0350 to the x over 1.117 to the x, and then our number. And so the value of those two numbers divided is 1.3593. You'll notice that both of them are raised to an x power, and so you can rewrite this as 1.0350 over 1.117 to its x power, which of course could be a decimal value. So let's see, 1.0350 divided by 1.117 leaves us with 0.9266 raised to an x power, and that's going to equal 1.3593 from the previous, yeah. And so then we can rewrite this as logs so that we can solve. So if we rewrite it as log base 0.9266 of 1.3593, that's going to equal x. And so we can solve for our x, or years. Oh, I see my issue. It turns out that there's supposed to be a 0 here. Hey, that's going to change my numbers. Okay, so it's not this value because we forgot a little 0 in there. Alright, let's see. Insert 0. Okay, so that means that our decimal value ends up being 1.0230. Because I was getting a negative number, which is not really possible if you're talking about years. Okay, so let's go back to the logs, 1.3593, and log of 1.0230. Oops, and then I pressed graph, that's funny. Okay. Alright, so that ends up being 13.5-ish, and so that means that we would add 1990 to it, and so we get 2003. Oops, could I just forget more zeros? Okay. And then does it ask for what the population is at that point? When would the populations of, yeah, so it doesn't actually ask what that population is, but you could plug in 13.5 as your x, and get the intercept value. Apparently it's at 741,862 people, if you're interested. Okay, so then number 54, assuming the growth is exponential, we need which city of Austin or Columbus would reach a population of 1 million first, and in what year. So all that means is that we are going to have 1 million equal to our two equations, so equal to 465, 622, 1.0350 to the x, and then also our other equation equal to 1 million, so 632,910. And as long as you followed the process in when we were going to reach 800,000, it's going to be the same thing. So we're going to divide by that initial population. So 1,123,123 divided by 465, 622 is 2.1477. And then if we rewrite this so that it's in log base 1.0350, we can find out that our x is going to be the log base 2. At least the way that I have to do it, and the other log 1.0350. Okay, so we're apparently getting 22.22. And again, plus 1990, the initial year that we're starting out at. That means in 2012 that Austin will reach, or did reach, 1 million. Okay. And then to the next one, 632,910. So we take our 1 million with 6 zeros after it and divide by 632,910 and get 1.58 equal to 1.0117. And then rewrite so that we have log base 1.0117 of 1.58. And that is going to equal our number of years. 58 and log of 1.0117. Alright, so apparently that is going to be in 39.32 years plus the year of 1990. So Columbus will reach that in 2029. So we have not reached that yet, because it is only 2020, at least when I'm making this video. Okay. Boop. Alrighty. So those are the last two. Sounds good.